Our next speaker is Professor Amritanshu Pandey from Carnegie Mellon. He's going to talk about dynamic graph-based anomaly detection in a power grid as well.
Hi, everyone. Thank you for giving me this opportunity to present some of the research that we have been doing at Carnegie Mellon. So, like Jawad, I'm going to focus on detecting anomalies on bulk electricity systems. So I'm talking about, there's the distribution grid, there's the transmission grid, there's generation. But what I'm going to focus on today is how to detect anomalies on the measurement data when we are thinking about electricity flowing from, say, Chicago to Pittsburgh. And before I move forward, I want to acknowledge all my collaborators. And the main work has been done by the lead author of this paper, Shimiao, who's in the audience today. And if there are questions that I cannot answer, I'm happy she'll be able to answer at the poster session. And I want to basically start with where we are today. So the way the grid is changing today is that the data on the grid is just rising exponentially. So we're collecting all this new data on the grid, and that's providing us with these great opportunities to use this data to do a lot of things. And so the kind of things we are beginning to do, and did in the past as well, is monitoring the grid, making sure that the elements that we care about are fine. Control of the grid, right, to make sure that we can use this data to make corrective actions when they're necessary. But we are also beginning to use it for things like policy making. I'm working on projects with folks in public policy, and we are looking at real-time data and data over historical data to provide policy recommendations to people. So the data has a lot more use cases today. One go back. Now, because this data is becoming more and more useful, it is also becoming increasingly important that we worry about the correctness and the accuracy of this data. So anomalous data is a growing challenge, and we need to come up with methods to make sure that we are able to identify anomalous data on the grid. So like I said, the focus of this talk is trying to detect anomalous measurement data in high voltage grids. And one might ask, why do you care about it? And again, I think Jawad did a great job of telling why it's so important. But this measurement data is used in the grid control room in two specific analyses, which is AC state estimation and topology estimation. And these analyses are extremely pivotal for day-to-day operation of the grid. Like Jawad said, the 2003 blackout, one of the primary causes of that was that the AC state estimation was not working. So we need to make sure that this measurement data is accurate. The problem, however, is that there are many reasons why this measurement data might not be accurate. We might have failures in the communication channel. We might have hurricanes, which might destroy the physical meters. And more increasingly, we are worried about things like cyber attacks. So while we haven't really seen a good coordinated attack on the real grid, people are worried that some adversary can conduct a coordinated attack on measurement data on the grid, and that could cause us to lose control of the AC state estimation, which would further result in all sorts of problems at the bulk control center. I'm not saying the grid would cascade, but it would be a big headache for the grid control room operators. So it's very important that we continue to work on methods that are able to detect this anomalous data on the grid. Now, there are already processes in place in grid control rooms. So if I were to go to ISO New England, which controls the New England grid, and tell them, listen, your measurement data is very important, and you should be able to detect anomalies, they say, we already do that. We have processes in place that do that. And the way it works is they take a single snapshot, time snapshot of the grid, and pass it through a bunch of analysis. And basically, this bad data detection tells you if there was anomalous data in the grid. And the idea is quite straightforward. It is understood, or it is assumed, that generally the measurement data comes with Gaussian noise. And if that is true, then the output of AC state estimation, one of the parameters, has a chi-square distribution. However, if I were to have certain measurement data that does not follow the Gaussian distribution, then I'll be at the tail end of that chi-square distribution, and I will flag that as an anomaly. The problem, however, is that now people are beginning to postulate some methods of changing this measurement data such that these processes don't work. And so the question is, what do we do about it? And Jawad mentioned one such method of basically taking the processes that we have in the grid control room today and improving on it. And I'm going to talk about another such method. And the idea is quite straightforward. Why do we only look at the single time snapshot? We have all this historical data that we are collecting. why then just care about single time snapshot? So can we just look at the historical measurement data, try to estimate what the distribution of that measurement data should look like, and if I fall on some tail of that, then you flag that as an anomaly. And of course, people in data mining have done immense amount of work to kind of do this kind of work. I'm being a power system person, can only help. But when I look at this as a power system person, I see a challenge. This assumes that all the historical data comes from a power grid setting that does not change, right? But the reality is much more different. Power grid is very dynamic. It is always changing. So what we have on the bottom right here is some results from the actual east interconnection of the United States. That's half of the United States, so you can think of it that way. And what we see is that we have roughly 12 to 15 switching of high voltage transmission line and transformers every hour. So that basically means that my grid is changing all the time. And so when I have changes in the measurements that are not necessarily anomalous, it could also be that my topology changed. And so if I were to just use generic anomaly detection using some sort of historical data, I'm likely to have a lot of false positives. And so I need to worry about that. And so the method that we have worked on is really trying to address that problem. And the idea is, can we incorporate the impact of topology changes into the anomaly detection algorithm, right? So the goal is, if I have a big topology change at 6 and time equals 6 and time equals 11, that I don't flag that as an anomaly because it's just a false positive. And so how do we do that? So we have a 3-step process to do that. We want to incorporate knowledge such that when we look at historical data, we put high confidence on the historical data that has a similar power grid setting as we have right now. And to do that, we have this graph distance methodology that we'll develop. Once we understand what power grid settings in the historical data are similar, we want to assign some sort of a weight to it. And then we use that weighted median and interquartile range to develop the anomaly detection algorithm. So let's look at how we develop the graph distance. So the idea is quite straightforward. We have a graph I, it could be some historical time set, and then we have a graph J, this could be the existing setting. And we want to know how similar these two graphs are. But I'm not looking at these graphs as someone who works with networks, does not care about the domain. I, being the domain person, I'm thinking, what makes two graphs similar in power systems? What makes two graphs similar in power systems is how is the flow of power in the system, right? I might not have an edge versus my flow might be 0 with the edge on. Those two are same events to me. So I'm really trying to incorporate the domain knowledge. And the way you do that is we develop the union of the graph, Gi and Gj, which we call the G trans. And then we identify all the edges that don't belong to either of these graphs and see how removal of those edges changes the power flow in different lines in the system. And then we sum them all up to get a graph distance. Now, if two power grid settings are very different, my graph distance is going to be very large. If two power grid settings are very similar, my graph distance is going to be quite small. So once I have the graph distances, now the question is, how do I weigh all the historical time ticks? So, well, one idea is, let's just use all the historical time ticks where the graph distance was very small. And if you do that, the model would have very low bias. But the problem is we might not have sufficient data, so my variance might be quite high. The other option is, you use all the time ticks, but then my bias might increase even though I decrease the variance. So we basically solve an optimization problem where we're trying to minimize both the bias and the variance at the same time with some hyperparameter C, and that's how we assign the weights. So now we have been able to assign weights to all prior historical time ticks. So that being done, now the question is, how do we detect the anomaly, or how do we develop an anomaly detection metric? And for that, we use median and interquartile range. And I asked this question to someone in statistics, why did we do that in first place? And the idea is that if you use median variance, that's not as robust at eliminating outliers in the historical data. And so by using median and IQR, we are able to be more robust if we already had some outliers in the historical data. And the anomaly detection score is actually quite straightforward. So you go to the measurement at each sensor, which could be x of t. You subtract from that the weighted mean and the weighted IQR, and that gives you an anomaly score. You do that for each sensor on the power grid setting, and you find the maximum of it. And if that maximum value is greater than certain threshold, then you flag that power grid setting as anomalous. And then you can go to the individual scores and try to find out which of those are actually causing those anomalies. So one other thing that I want to talk about briefly is if you look at what I spoke about right now, and I said, we basically try to calculate two graph distances. So if I have a graph GI and I have a graph GJ, I basically identify what the graph distance is. And if the graph distance is very high, I put low confidence on all the measurements at that historical time tick. But if I think about it a little bit more from the domain knowledge, say this represents New York City and this represents Florida. If I have some kind of outage in New York City, from experience, I know that that should not impact my sensor readings at Florida so much. So rather than having one graph distance for all possible sensors, the idea is, can we actually have local graph distance, because I have some understanding of how the change in power diminish as I go further along the system. And so we basically try to develop a local sensitive graph distance. And in this case, we have a specific graph distance corresponding to each sensor. And this provides us slightly better results. So here's an example, and it might be quite complex in terms of figure. So what I have on the top left are a set of measurement streams, synthetic measurement streams. And you see 5 vertical lines, 3 of which are red vertical lines. And those actually represent synthetic anomaly that we have injected into the system. And then we have black vertical lines. Those are the topology changes. And we have 3 methods to detect these anomalies. And the first method is what we have in the control rooms today. This is the weighted least square. We look at the residual value and say if there's an anomaly or not. But these anomalies were particularly constructed so as to beat that. And this is the work on false data injection attacks that a lot of people have worked on. And we see that this approach is not able to detect all the 3 anomalies. Well, then we look at a classical anomaly detection based on temporal data. And we see the problem with that is, yes, it detected all the 3 anomalies, but it also gave us false positives corresponding to the 2 topology changes. So we have false positive that we did not want. However, when we use the proposed approach, we are actually able to detect only the 3 anomalies without any false positives. So here are some other results, and I think the key point to take away is really showing some sort of a comparison. And what we see here is that the DYNWATCH, or the proposed method, tends to have better anomaly detection metrics in comparison to other classical approaches. But again, that makes sense because we're including a lot of domain knowledge into our methodology, so it should work better for this domain. And the main key result over here is we run state estimation, and we're likely to run state estimation in the future every minute or so. So any anomaly detection algorithm we develop should be faster than time range of a minute. It should be in 15 seconds or 20 seconds. And this is just basically saying that, yes, this anomaly detection method is pretty fast, and so we can actually use it in the real-world setting. So with this, I would just like to conclude my talk, and I just want to point out that growing dependence on electric data is raising concerns about correctness and accuracy of that data. So this topic is becoming more and more increasingly important, that when we make decisions on data, that we actually check that this data makes sense, and that there is value in the field of people who have been studying with statistics and machine learning, coming together with folks who understand the domain and kind of develop collaborative methods to target challenges in this space. Thank you.
Are there any questions?
Thank you. Great talk. Lars Nordström, Electrical Engineering, KTH. I was curious about this graph distance. You mentioned it briefly that you were not just looking at the actual connectedness, but the power flows. But what's the computational load there to be able to do that in detecting these topology changes?
So, I mean, and you're absolutely right. So there are two ways to do it. Either I can run power flows, but that is, you're solving 10 iterations for each. So what we use is line outage distribution factors. So we are using linearized version of power flow. And this is actually used, and the idea is I can take off a line, and solving this linear problem, I can tell you how much percentage does the flow in every other line changes. And the concept is called distribution factor. So this is much faster than running the actual power flow each time.
Thanks.
Thank you for a nice talk. Jordan, KTH, also electrical engineering. I wonder, now that we know your anomaly detection scheme, how would we construct an attack that bypasses your scheme?
Yeah, I guess that should be our next paper. But yeah, I mean, I'm sure there are chinks in the in the method, but I haven't really thought about it that way. But it's a very great question. I should think about it. But I'm sure Cindy over here knows the answer to that, because she's thought about this method in every possible way.
Are there any other questions? Just they're going to put up some chairs for the, yeah. Okay, if there aren't any, let's thank the speaker again. Amritansh, thank you.